In this lecture, we'll close our explorations into analytic number theory by studying its crown jewel, the prime number theorem, which answers the delicate question, can we estimate how many primes there are up to a certain size? Well, this question continues to be one of the great questions in mathematics and of great interest to mathematicians today. To improve the estimates within this important result, we'll return to Euler's general product formula and come face to face with a notoriously difficult open problem known as the Riemann hypothesis, one of the most important unsolved problems in all of mathematics. The truth of the Riemann hypothesis would immediately imply a long list of deep mathematical results. While the issues surrounding the Riemann hypothesis first appear to be totally divorced from our real world, we'll mention some tantalizing new connections with physics through what are known as random matrices. Thus, perhaps some modern ideas from physics might hold the key to unlocking the mysteries of this long-standing open question about the atoms of the natural numbers, namely the primes. While a complex proof of the prime number theorem was found in 1896, many number theorists wondered if there was a so-called elementary argument. Finally, in 1948, an elementary proof was found by two great mathematicians, the prolific Hungarian mathematician Paul Erdős and the influential Norwegian mathematician Atle Selberg. As we'll discover, this mathematical milestone led to one of the most famous disputes in all of number theory history. We'll close this chapter of our course by describing some modern advances in the study of primes, some of which will involve the concept of arithmetic progressions, which we actually saw earlier together. Finally, we'll describe some famous questions involving prime numbers that have confounded number theorists throughout the ages and remain as mysterious today as they were when they were first considered. Well, we close our study of the primes by returning to Euclid's theorem, stating that there are infinitely many primes, and we prove that for ourselves. The question we now wonder is, can we make this result more precise? A common theme in mathematics. Once we have a result, can we somehow sharpen it or improve it? Well, to allow us to discuss the number of primes up to any given point, we'll write the symbol pi of n to denote the number of primes less than or equal to n. Now here, pi of n has nothing to do with the famous number pi from geometry and circles. Pi of n is the name of a value, the value meaning the number of primes up to a particular value of n. So it's a symbol that number theorists use. So for example, pi of 25 would mean the number of primes there are up to 25, and that would equal 9. So pi of 25 is the number 9. Why? Because there are 9 primes that are less than or equal to 25. And in fact, they are 2, 3, 5, 7, 11, 13, 17, 19, and 23. And you can see there are 9 of them. Euclid's theorem asserts that pi of n approaches infinity as n gets larger and larger. Notice how this is the way to phrase Euclid's result using this pi of n symbol, because Euclid proved that there are infinitely many primes, which means that as n gets larger and larger, the pi of n should eventually get larger and larger as well and approach infinity. So we're now led to a very natural question in number theory. Is there a formula for pi of n? Meaning, is there a formula to give how many primes there are up to any given point? Well, this remains an open question whose answer appears to be totally intractable. Well, by the late 18th century, French mathematician André-Marie Legendre and the great Gauss made an amazing discovery. They observed that the number of primes less than or equal to n seems to be connected with the so-called natural logarithm function. Now, the natural logarithm is the logarithm with a very special base number, e. That's a special number that's approximately 2.71828 and so on. Well, the value of the natural log of n for any n can be found using a scientific calculator, just using the button that's called ln, which stands for natural log. Now, a logarithm, in essence, is an exponent. And so, for thinking purposes, we can view the natural log of a natural number n to be, roughly speaking, twice the number of digits n contains. So, for example, if we want to find look at a million, for example. Now, how many digits are there in the number a million? Well, there's 7 digits. And if we take a look at the natural log of a million, what we actually see is something that's roughly 13.8 something. So notice that 13.8 is roughly twice the number of digits. There's 7 digits, double it, we get 14, and the natural log of 1 million is actually 13.8 something. So you can see, roughly speaking, it's about that. Anyway, this rough intuitive notion is certainly enough for us to see that the natural logarithm function is a very slow growing function. Notice that when we get to a million, the value of the function is only around 14, so it's very, very slow growing. That's all that matters for us. Well, the conjecture of Legendre and Gauss was that as n gets larger and larger, the number of primes up to n gets closer and closer to the function n divided by the natural log of n. And we could actually look at some data here to see this for ourselves. So for example, if we let n equal 100, then pi of n, the number of primes there are up to n, equals 25. There are 25 primes that are less than or equal to 100. And if we now compute 100 divided by the natural log of 100, we see a number that's approximately 21.7 something. And so you can see that 25 and 21.7 are relatively close together. It's a pretty good estimate. If we go out further, we get a better estimate. For example, if we let n equal a million, what's pi of 1 million? That asks how many primes are there up to 1 million? Well, it turns out that's exactly 78,498. That's how many primes there are. And what happens if we compute the other quantity, 1 million divided by the natural log of a million? Well, that works out to be 72,382.4 something. And so you can see these quantities are actually very close together in terms, especially in view of their size. Well, how could we see if these two quantities are genuinely approaching each other? Well, let's think about this for ourselves. If two non-zero numbers are equal, we know that their quotient would equal 1, because a number divided by itself is 1. So we can ask, what if we look at the number of primes up to n, so pi of n, and look at the ratio between that and this quantity n divided by natural log of n? Well, if that ratio is approaching 1, then we could see that these two quantities are in fact approaching each other. And in fact, we could try this with the 1 million example. If we take a look at n equals a million, and take a look at the number of primes there are up to a million, and look at the ratio of that number to 1 million over the natural log of 1 million, then we'd see a ratio of 1.0844 something. Very, very close to 1. Therefore, these quantities are in fact getting closer to each other, it appears. Well, the great Russian mathematician Pafnuty Chebyshev proved in 1850 that if this ratio of pi of n to n over the natural log of n approaches some number as n gets larger and larger, then that number must equal the number 1. It's a very strange result. It says that if these values get closer and closer together, then in fact they're heading toward the same value. So if the ratio is getting closer to something, then in fact it has to be getting closer to 1. Kind of strange. But 9 years later, in 1859, the great German mathematician Bernhard Riemann introduced a number of revolutionary ideas in his memoir entitled On the Number of Primes Less Than a Given Magnitude. Among other things, he showed how this issue is connected with complex numbers. Those are numbers involving the imaginary number I, which equals the square root of -1. And also he connected it with the zeta function that we saw earlier, zeta of s, that actually appears in Euler's general product formula from the previous lecture. In fact, today the zeta function is actually known as the Riemann zeta function in honor of Riemann. Finally, in 1896, French mathematician Jacques Hadamard and Belgian mathematician Charles de la Vallière-Poisson independently produced a proof of the prime number theorem. In other words, they proved that as n gets larger and larger, the number of primes up to n is approaching n divided by the natural log of n. Or more precisely, as we've just seen, as n gets larger and larger, the ratio pi of n to n over natural log of n approaches 1. Well, so the prime number theorem implies that as n gets larger and larger, the number of primes gets closer and closer to n over the natural log of n. However, for any particular value of n, pi of n is not equal to n divided by natural log of n. There's an error given by the difference between these two numbers. This error is often actually referred to as the error term. So a natural question remains. How close are these two numbers, the number of primes up to n and n over the natural log of n, in actuality for larger and larger values of n? In other words, how small is the error term? Well, in Riemann's famous work, he found a profound connection between the number of primes up to n and that zeta function, zeta of s, which equals 1 plus 1 over 2 squared plus 1 over 3 squared, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, plus 1 over 5 to the s, and so on, that endless infinite series. Riemann's insight was to extend this series, the zeta of s series, to allow s to be a complex number. That is, he allowed s to equal a number of the form x plus I multiplied by y for decimal numbers, or real numbers, x and y, and I equaling the imaginary square root -1. Now, what does it mean to have an imaginary exponent? Well, while the answer would certainly take us far off topic here, let me just say that it was Euler himself who made this idea precise. In fact, he derived one of the most amazing formulas in all of mathematics that actually includes such an imaginary power. He proved that e, that special number we saw before, raised to the power pi times I, is actually equal to -1. Profound and perplexing. Notice that by raising a positive number like e, which is like about 2.7 something, to an imaginary power, we can actually get a negative number as an answer. Very bizarre. Well, in fact, imaginary exponents do have meaning in an abstract sense, and I'll just leave it at that. Riemann studied the complex numbers s that were solutions to the following very strange-looking equation. Zeta of s equals 0, or equivalently, but even stranger looking, 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s plus 1 over 5 to the s and so forth forever equals 0. Well, if we let s be a natural number like 2, we see that the left-hand side will clearly be some positive number and will never be 0. But as we just saw a moment ago, if s were to be imaginary, then some of those terms might in fact be negative, and we might have that sum collapsing to 0. Well, Riemann proved that all the complex solutions s to this equation, when written as s equals some decimal number x plus I times some other decimal number y, would always satisfy the condition that that first x that we add in the solution is always a number that's between 0 and 1. So it could be 0 all the way up to 1. And he showed that these bounds, that if in fact these bounds could be improved, which means if we could tighten those bounds and restrict the x even more, then the error term in the prime number theorem could be dramatically reduced, which is of course what we're after. Well, in fact, the key step in Hadamard's and de Vallière-Poisson's proof of the prime number theorem was showing that all solutions x, written as x plus I times y, to Riemann's equation, actually satisfied a slightly stricter condition. The x value actually had to be strictly larger than 0 and strictly smaller than 1. So instead of being between 0 and 1, in fact, instead of being between 0 and 1, we actually see that it has to actually be strictly inside that region. It can't equal 0, can't equal 1, and that's how they were able to prove the prime number theorem. Okay, well, Riemann himself conjectured that all the solutions to this particular equation actually satisfied that x equals a half. So in other words, when we take a look at the interval, all the x's lie right in between. There's no need to move around at all. Everything is right in between. Those x's lie on this point right here at a half. Now, this famous conjecture is now known as the Riemann hypothesis. Well, what if it's true? What if the Riemann hypothesis is true? Well, if it were true, then we would have a much smaller error term in the prime number theorem. In addition, we would learn an enormous amount about the prime numbers, because there are literally hundreds of theorems that actually begin by saying, assuming the truth of the Riemann hypothesis, blah-de-blah-de-blah-de. And so if we knew the Riemann hypothesis were true, then we would have some interesting results about the primes as well. Well, in 1900, the great German mathematician David Hilbert included the Riemann hypothesis on his list of the 23 most important unsolved questions in mathematics at the dawn of the 20th century. 100 years later, the Clay Mathematics Institute in Cambridge, Massachusetts, listed it as one of its millennium problems. A correct and complete answer would actually result in a prize of $1 million. But let me just suggest that there might be a lot easier ways of making $1 million. This question is genuinely hard. And in fact, it remains one of the most important open questions in all of mathematics today. Well, much work has been done, as you could expect, in this direction, and there's a long list of partial results surrounding the Riemann hypothesis. There's even computer evidence supporting Riemann's conjecture. In fact, from 2001 through the year 2005, a number theory program called Zeta Grid verified that the first 100 billion solutions to Riemann's equation had, in fact, the x value equaling a half, as Riemann himself conjectured. Of course, this data, however overwhelming, is not a general proof. Now, very recently, an intriguing and exciting connection has been made between the Riemann hypothesis and quantum physics. A new direction toward a possible proof of the Riemann hypothesis might be through the study of objects called random matrices. These are mathematical objects that were originally applied to better understand the quantum behavior of larger atoms in physics. Well, wouldn't it be wonderful if mathematical models that allowed humankind to better understand the atoms of physics also allowed us to gain insights into the atoms of the numbers, namely the primes? Well, let's now return to the prime number theorem, which tells us that as n gets larger and larger, the number of primes up to n is approaching n divided by the natural log of n. Now, the original proof of this theorem was extremely clever and subtle, especially in demonstrating that the x value is always strictly smaller than 1 for all the solutions to the Riemann equation. In 1921, the great British analytic number theorist G.H. Hardy wondered if an elementary proof of the prime number theorem could be found. In other words, a proof that only involves very simple properties of functions, but in a very, very extraordinarily ingenious manner. So don't use any high-powered math machinery. Use simple machinery, but in a very, very clever way. The proof of the prime number theorem that we've discussed actually used very sophisticated machinery to prove a fact about the prime numbers. Well, 27 years later, in 1948, Paul Erdős announced that he and Atle Selberg found a truly elementary proof that only involved basic properties of logarithms. Well, this announcement stunned the mathematical world. And let me say a few words about these two great mathematicians with very different personalities and temperaments. In some sense, they were really the odd couple of analytic number theory. Paul Erdős was a Hungarian mathematician who published well over 1,500 mathematical articles with over 500 co-authors, collaborators from around the world. He was a mathematical nomad, if you will, having no true academic affiliation for most of his life. He would travel from institution to institution. He would show up at math departments, and he was very famous for showing up at a math department and just walking in and saying to his mathematician friends, "My brain is open," which means, what are you working on? What are you thinking about? Let's talk math. And that's why all those papers were written and why he has so many collaborators. Well, his prolific and foundational work inspired and fed new branches of mathematics, including areas called graph theory, combinatorial number theory, and elementary number theory, those last of which we saw earlier in the course. Atle Selberg was a Norwegian mathematician who spent most of his time and his career at the very prestigious Institute for Advanced Study at Princeton. He produced very profound results in advanced areas of number theory, including so-called automorphic forms, and introduced several new areas of study, including the Selberg sieve, which is similar to the sieve we discussed, but far more advanced, and also what's called the Selberg trace formula, very, very complicated and important formula. Well, their proof of the prime number theorem was so sensational that in 1950, Selberg was awarded the Fields Medal, which is the mathematical equivalent of the Nobel Prize. And in 1952, Erdős received the Cole Prize, one of the most prestigious prizes in mathematics. This mathematical partnership was both unusual and extremely tense. In fact, a serious controversy arose over who should receive credit for what part of the proof. Well, here's a little bit of a brief account of the soap opera-esque drama. In March of 1948, Selberg discovered an important formula involving primes, but didn't publish it. Several months later, Selberg shared with Hungarian mathematician Paul Turan an inequality he discovered, now known as the fundamental formula. Now, without Selberg's objection, Turan gave a lecture outlining Selberg's recent work. Erdős, who was in the audience, quickly noticed, and he said, I think that you can derive the fact that the ratio of consecutive primes is actually approaching 1 as we go further and further out, and we can derive that just from this inequality. And in fact, within a few hours, Erdős produced an ingenious proof of this extremely important assertion. A day later, when Erdős actually shared this news with Selberg himself, Selberg totally was dismissive and responded with, "Oh, you must have made a mistake," because implying that certainly such a deep result that Erdős claims couldn't follow from this little inequality that Selberg had. Well, a few days later, Selberg, using his formula involving logarithms and primes, together with Erdős's important result, was able to devise an elementary proof of the prime number theorem. The key ingredient, however, was Erdős's theorem. Well, Erdős suggested that the two collaborate and write a joint paper. However, Selberg suggested that each should write their own papers based on their own work. Now, Erdős found this objectionable since this was genuinely an example where the whole was tremendously greater than the sum of the parts, meaning that this result was so enormous that the individual pieces weren't as dramatic as the actual consequence. Well, to make matters worse, news started to spread about the amazing breakthrough. Now remember, Erdős traveled all over the place and knew everybody. But the rumor actually attributed the result to Erdős himself. In fact, there's a story that in the fall of 1948, someone greeted Selberg with the exclamation, "Have you heard the exciting news, what Erdős has proven?" Well, this did not help the situation. Well, the two did publish their papers separately and mention each other's work. However, they no longer spoke to each other after that point. Finally, 45 years later, in 1993, at a conference in Hungary to honor Erdős's 80th birthday, much to everyone's surprise, Selberg not only attended the conference, but also delivered one of the lectures. And I actually happened to be attending this conference and actually spoke at this conference and witnessed this myself. And everyone at the conference thought this was the greatest moment in mathematics at that time, that these two great mathematicians were finally reconciling, toward the end of their lives. Little did we know that at that exact same moment, at a different conference in England, even greater news was about to break. And I'll mention this when we talk about Fermat's last theorem in a future lecture. Well, the prime number theorem gives us an estimate for how many primes there are up to any particular point. In some sense, it tells us something about how the primes are distributed. In view of this result, we can consider other advances regarding the distribution of the primes. And to do this, let's recall the idea of an arithmetic progression that we saw earlier together. We start with a number and then continue to add a fixed amount. For example, if we start with 1 and repeatedly add 17, then we would obtain the arithmetic progression that begins 1, 18, 35, 52, and so forth. Well, Gauss himself wondered if such arithmetic progressions always contained prime numbers. Now, in this example, we have 1, 18, 35, 52, 69, 86, 103, and 103 is the very first number on this list that's actually prime. So we had to go all the way to 103 to actually find a prime. Well, in 1837, German mathematician Johann Dirichlet proved that given any natural numbers a and b that don't share any prime numbers in common as factors, so they share no prime factors, then the arithmetic progression we get, which starts a plus b, a plus 2b, a plus 3b, a plus 4b, we keep adding b each time, and so on. This arithmetic progression will not only contain a prime number, but will always contain infinitely many prime numbers. And notice how beautifully this extends Euclid's original theorem about the infinitude of primes. Euclid proved that in the simple arithmetic progression 1, 2, 3, 4, 5, 6, and so forth, that contains infinitely many primes. Now, Dirichlet proves that, in fact, any arithmetic progression, as long as the a and the b have no common factors, any such thing will contain infinitely many primes. A dramatic improvement. In a related but different direction, suppose that we list all the prime numbers in order. So 2, 3, 5, 7, 11, 13, 17, 19, and so forth. Within this list, do we see any pieces that form an arithmetic progression? Well, the answer is yes. For example, 3, 5, 7 forms a little arithmetic progression because we just have to add 2 each time to get the next one. Well, what's the longest arithmetic progression found in the list of primes? Recently, in 2004, some groundbreaking work was done in this direction by Ben Green and Terence Tao. They proved the astounding result that there are arbitrarily long arithmetic progressions within the list of prime numbers. So any length you can think of, if we look far enough down, we'll find an arithmetic progression of that length. And in 2006, Tao was awarded the Fields Medal for his spectacular work relating to the primes and his work related to number theory in general. In spite of all that we know about the prime numbers, there are still far more prime number mysteries yet to be cracked. So we close our discussion on analytic number theory by mentioning some famous, or should I say infamous, open questions involving the primes. The first question is called the twin prime conjecture, which asks, are there infinitely many pairs of primes that differ by 2? So for example, 3 and 5 differ by 2. 5 and 7 differ by 2. 11, 13 differ by 2. These are known as twin primes. Notice that the pair 13, 17 is not a pair of twin primes because their difference is 4. The twin prime conjecture states that there are infinitely many twin primes, but the proof actually eludes all of us for now. Notice that this would also extend Euclid's result in a different direction. Next, we turn to what is known as Goldbach's conjecture. The Goldbach conjecture asserts that every even number greater than 2 can be written as the sum of 2 prime numbers. We notice that 6, for example, is 3 plus 3, the sum of 2 primes. 12 equals 5 plus 7. And even something like 74 equals 31 plus 43, sum of 2 primes. Well, this conjecture was first made by Christian Goldbach in a letter to Euler dated back June 7th, 1742. And despite the fact that the conjecture has been shown to hold for all even numbers up to around 3 times 10 to the 17th power, that's huge, a proof that it holds for all even numbers has yet to be found. And finally, just for fun, I want to mention the gigantic number known as Skews number that I mentioned actually at the beginning of the course. Now, we've seen that the number of primes up to n, that as a function, approaches the function n divided by the natural log of n. However, there's another function called the logarithmic integral, which I won't define here, which is written as Li of n, with the property that the pi of n function minus this logarithmic integral function actually approaches 0 as n gets larger and larger. Now, it never actually equals 0, it just gets closer and closer to 0. So since we're subtracting these two quantities, the sign will either be positive or negative, depending upon which is larger. Well, in 1914, the great British mathematician John Littlewood proved that the quantity pi of n minus the logarithmic integral of n changes from positive to negative infinitely many times. So it keeps toggling back, which is bigger, but the difference is heading towards 0. But you wiggle back and forth between positive and negative. However, for all values up to around 10 to the 22nd power, the quantity has been shown to be negative. In other words, the logarithmic integral was always larger than the number of primes for all n up to around 10 to the 22nd power. Well, given Littlewood's result, however, we know that the logarithmic integral must at some point become smaller than the number of primes from that point. But when? Well, it was the South African mathematician Samuel Skews in 1933 who proved that assuming the truth of the Riemann hypothesis, so we're assuming the Riemann hypothesis, the logarithmic integral must be smaller than the number of primes for some n less than, and here's that enormous number, 10 to the power 10 to the 10 to the 34th. Well, this incredibly large bound is now known as Skews number and was described by G.H. Hardy as the largest number which has ever served any definite purpose in mathematics. The primes continue to capture the imagination of individuals from around the world who continue to uncover the primes' many mysteries. And mysteries, of course, remain. Erdős once said, referring to Einstein's famous quote, "God may not play dice with the universe, but something strange is going on with prime numbers." I hope you enjoyed thinking about the deep ideas of the primes.